We're now going to turn our attention to Java platform threads versus Java virtual threads. In part one of this lesson, we'll explain the differences between Java platform threads and Java virtual threads. Platform threads are typically mapped one-to-one onto kernel mode threads that are scheduled by the underlying operating system. Conversely, virtual threads are typically user mode threads that are scheduled by the Java execution environment. A Java thread has traditionally been an object that contains various methods and fields that constitute its state. For example, each Java thread historically had its own unique name, which is a string, a unique identifier, which is a number, a priority that's used to differentiate between different threads to decide which ones get to run before the other ones, a runtime stack that also has a kernel-level component, thread local storage, and various registers, such as an instruction pointer, a stack frame pointer, and so on. Very modern Java, in other words, Java 19 and beyond, refers to these types of Java threads as platform threads. Each Java platform thread is associated one-to-one with an operating system kernel thread. It therefore contains the same unique state as a traditional Java thread object, such as a name, identifier, runtime stack, and so on. Platform threads are suitable for executing all types of tasks, be they CPU-bound tasks or I/O-bound tasks, and so on. Historically, they've been particularly useful for I/O-bound tasks that block reading and/or writing on sockets and/or files, because those blocking threads can be put to sleep by the operating system and other threads can be scheduled to run in order to be able to perform the operations while some threads block. This particular example is something we'll take a look at later in the course, which demonstrates how you can apply Java threads to download images and display them in the context of an Android application or a Java console application. However, platform threads are a limited resource due to their non-trivial runtime stack size. There are different stack sizes by default on different platforms. This link at the bottom of the slide gives you a summary of some of the default sizes on Windows and Linux and so on. But the key point is that it's not a trivial amount. It's typically 512 kbytes or a megabyte or so on, depending on different properties. Moreover, Java platform threads may need to synchronize whenever they have to coordinate their activities or prevent race conditions. And synchronization may cause an expensive context switch to happen between operating system threads, depending on various factors, such as whether the synchronizer will put the thread to sleep, awaiting the completion of some long-running coordination operation. Let's turn our attention now to an overview of Java virtual threads and compare and contrast them to Java platform threads. Each Java virtual thread is a lightweight concurrency object. So whereas the platform threads are all puffed up on steroids with big muscles, a virtual thread is much leaner in contrast. In particular, a virtual thread is a so-called user thread rather than a kernel thread. And what that means is that a virtual thread is scheduled by the Java execution environment rather than being scheduled by the underlying operating system kernel. As a consequence of this, a very large number of virtual threads can be created. You can have millions and millions of virtual threads. In contrast, trying to spawn and run millions and millions of Java platform threads is prohibitively expensive on all but the most resource-capable operating system and hardware platforms. Virtual threads are therefore multiplexed atop a pool of so-called carrier threads. A carrier thread is essentially a platform thread that has some other properties. As a consequence, blocking operations in a virtual thread will no longer block the underlying carrier thread, and that therefore enables a very large number of requests to execute in parallel upon a much smaller number of carrier threads. There are typically roughly about as many carrier threads as there are cores on a Java execution environment platform. And you can see here how this diagram demonstrates where we've got one carrier thread and 3 virtual threads, and the carrier thread is used to keep the virtual threads running, even though some of the virtual threads are blocked and are waiting at various points in time for certain operations to complete, typically I/O operations like reading or writing from a socket or reading or writing from a file. The Java fork join framework is currently used to implement these carrier threads. And the Java fork join framework is a very powerful framework that allows a smaller pool of platform threads or carrier threads to be used to perform the computations of many, potentially hundreds of thousands or millions of virtual threads that are multiplexed atop it. More information on the Java fork join framework is available online. For example, if you go to the link at the bottom of this slide, you'll find many other videos that explore other dimensions of the Java fork join framework's advanced features, such as its support for work stealing, which enables idle worker threads to steal work from busy threads, thereby enabling the maximum utilization of the underlying processor cores. Likewise, the common fork join pool in the Java fork join framework supports something known as managed blocking, which helps avoid starvation and improve performance by adding new worker threads to the pool of worker threads whenever existing threads in the pool block. These capabilities not only work in support of Java virtual threads, but they can be used in their own right for other Java concurrent and parallel applications. So this is the end of part one of our discussion of Java platform threads versus Java virtual threads.